So you want to verify the two functions are inverses of one another. All you need to really do is substitute one of the functions inside of the other one for x. All right. So the notation was a little heavy last time, but it really is the idea that you're going to plug one function into another or into the other, simplify, and actually let me be a little bit more specific for that, into the other for x, simplify, and see if you get x as a result. If so, the two functions are inverses. All right. So this is just really a verbal way of explaining what I talked about last time, because I realized, belatedly that, notation is a wonderful thing. It's a nice, easy, shortcut way of representing something in terms of, a definition, a property, a procedure, or something like that, some kind of method that we're using to solve a problem. But if you don't know what the notation means, it doesn't do you much good. All right. So what this means symbolically is that we're going to take the f function and replace the variable x with g of x. All right. And if that is equal to x, then f and g are inverses. So this is kind of a more shorthand way of saying the same thing. All right. So what I want to do here is I got my f of x and my g of x. I'll rewrite the f of x. I'm going to replace the x in each case with g of x. All right, so everywhere I have an x in that original function, I'm replacing it with a g of x. And then I'm going to replace g of x with what it really is. On the left-hand side, I could do that, or I could just leave it using the notation. I'm going to leave it using the notation f of g of x. But on the right-hand side, I'm actually going to substitute in the g of x expression, which is negative 2x plus 6. And if you remember from whatever your last algebra class was, composite functions, plugging one function into another, this is actually, it's not the only reason why you would do that, but this is one of the reasons why. Okay, so that we could verify whether two functions are inverses. And then in calculus, you'll do more with that, with something called the chain rule. So, if you happen to remember that when you're in that moment, you're like, oh, chain rule. We're learning about that. That was the thing you talked about back in pre-calc. Then you're going to be in a good spot. All right. So I'm going to take this negative 1/2 and distribute it to each part in the blue here. And that's going to give me x minus 3. I have that plus 3 coming along for the ride here. I'll just do that in red. The result here, negative 3 and positive 3, are going to cancel out to just x. And so that's actually my rule. If this is a true sentence, f of g of x is equal to x, then the functions f and g are inverse. So conclusion, f and g of x, or so I could just say f and g, are inverses. And so that's really it. But, now that I'm thinking about it, I didn't show you a case where it doesn't work out. So let me make up another example. And you see, I got my little note here, make up another example like number 4. All right, so I'm going to just kind of bring this down a little bit. Give myself a little more wiggle room here. So let's say we have number 6, and it's f of x is equal to, it really doesn't matter. Let's say x squared, because I don't need it to work out. I'm showing you a case where it doesn't work out. So let's say x squared plus 3, and g of x is equal to 5x plus 2. All right, so what I would do is determine what f of g of x is. All right, so f of g of x is what I'm going to get if I replace every x in the original f function with whatever g of x is. All right, so I'm getting f of g of x is equal to g of x squared plus 3. All right, and since g of x is equal to 5x plus 2, I can make that substitution. But again, I only want to make that substitution on the right-hand side because the notation on the left-hand side is helpful in verifying what procedure we're actually following. All right, so I'm going to replace the g of x on the right-hand side. You might remember this from algebra class, where the left-hand side, when you're dealing with composite functions, left-hand side is kind of like the recipe that you're following. The right-hand side is you carrying out the process that's in the recipe. The recipe is plug g of x into f of x. On the right-hand side, we actually carry that out. All right, so we get 5x squared. Oh, I didn't want blue here. Go red. 5x squared plus 2. That's my g of x. And if I could do whatever I want to this, but if I want to simplify it, I probably have to distribute it out. But it's okay to stop at this point, because there's no way, even if you distributed it out, the 5x plus 2 squared, you're going to get a quadratic. There's no way you're going to end up with an x, just an x. The whole right-hand side has to simplify down to just an x. If you realize at this moment that there's no way that could happen, then you would just say f of g of x is not equal to x. And so the conclusion would be f and g of x are not inverses. So f and g are not inverses. All right. Now, just in case you don't recognize that, I'm going to show you real quick. If I take this and just kind of bring it off onto the side here, 5x plus 2 squared is the same as 5x plus 2 times 5x plus 2. And then we still have the plus 3 there. We'd use the distributive property. So you might have heard of this, FOIL this out, distribute this out, double distribute. It's got so many different names, but it's all distributive property. So 25x squared plus, you'll have 10x on the outers, 10x on the inners, so 20x plus 4 plus 3. So that simplifies down to 25x squared plus 20x plus 7. That's not equal to x, and it could never be. All right, so either way, f and g of x are not inverses. If you get to this step here and you're just not sure and you're not really confident with your algebra skills, remember, it's not an algebra class. So use technology. All right, as much as I want to say how valuable it would be for you to strengthen your algebra skills. If it doesn't happen, you need something to fall back on. All right. So let me bring up my numworks here, which is kind of frozen on me for some reason. So let me shut that app down. Actually, my whole screen just froze. It's still right though. All right, let me do this real quick. Oh, I just pushed the home button and now it works. I have no idea why. All right, so go to Grapher. This is from last time. But I'll go expressions, get rid of this, get rid of this. I'll put in this expression here as a y equation. So I'll say y, so alpha 3 to bring up a y. All right, so it's in the keypad here. So this button here is what we want to bring up the y. So alpha, that button. All right. Then I want equal sign, so shift pi. All right. Sometimes I accidentally hit the alpha button first and it brings up a J. So try that again. Shift pi. Okay. Let me try that 7 or 8 more times. Actually, let me clear this out. Because when I long pressed on the alpha, I think it just locked it in. All right. So alpha 3. Alpha. Now my alpha doesn't want to work. There it is. Shift pi. Then paren 5x plus 2. Close it up. Squared plus 3. All right. So that's just some equation, y equals 5x plus 2 squared plus 3. Now I want to compare that to y equals x. All right. So compare to y equals x. If they're the same, then you have it. That means that they're inverses. Graphically. If they're different, then they're not inverses. So I would just type in alpha y, or so alpha 3 brings up the y, shift pi equals, bring in the x. All right. Then I'm going to hit OK. I'm going to look at the picture. If you don't want to look at the picture, you can look at the table either way. The pink is the parabola. That's the 5x plus 2 squared plus 3. The orange is the line, which is not the same as the parabola. So they're not inverses. So you could also look at it that way, right? After you do your composite functions. The only reason I'm not saying just put the original equations into the calculator and compare them is because you're going to need to do this algebraically. All right. So it's one thing to look at two graphs and say, oh, they're inverses. It's another thing to justify it algebraically. All right. So that's kind of the end game there. So we're going to move on, and we're going to talk about exponential functions. Exponential log functions in and of themselves are not complicated, at least as far as the calculator is concerned. Sometimes it can be a little tricky to understand under what circumstances you use a log or an exponential function. In other cases, it could be tricky to actually carry out the algebraic approach involving exponential functions and logs, but the act of graphing them should not be difficult. All right. So I have some notes here. For any real number x, an exponential function is a function with the form of f of x is equal to a times b to the x power. All right. And I'm just gonna really exaggerate that for a sec. So what this means is f of x is equal to a times b to the x. All right. So, and you might look at that and say, well, you did not add anything to the conversation here. Yeah, obviously. But what I'm saying really in a nutshell is only b is raised to the power of x. right? So only b is raised to the power of x in this model. The a value, it takes on a few different roles. You can look at it as a constant multiple, but it's really ultimately going to end up being the y-intercept of the function, right? So, and I make a note of that down here. The y-intercept is 0a. You have a horizontal asymptote for this pair. There's a parent function associated with this, and that parent function will have a horizontal asymptote of y equals 0. All right. And so ultimately, what it's going to look like if I just do a quick rough sketch. So, oop, that was not a good arrow. There we go. Better arrow. A quick rough sketch for an ordinary untransformed exponential function is going to look something like this. All right. With this being a. The b value they call, well, again, it's another one of those instances where it takes on different names. So the b value is the common ratio. Also known as the base. All right. So the b value is a common ratio, also known as a base. It gives us a sense of the rate of increase of the function. All right. So it's going to vary from problem to problem, because sometimes it's going to decrease in height, sometimes it's going to increase in height. It all depends on how the function is transformed. All right. So in number 1, I say sketch a graph of f of x is equal to 0.25 to the x. You can make a table of values. You could also use some of what I'm saying here, like we could figure out what the y-intercept is, because this is the same as f of x is equal to 1 times 1/4 to the x power, or 0.25 to the x power if you just want to work with the decimal form. So I can get the y-intercept out of this. Let's bring it in real quick. All right, so I know it's going to cross the y-axis of that location, right? But what's happening is with that 1/4, for every increase in x, the y value is going to get cut based off of the base value, So it's basically, it's going to be 1/4 of the previous value, right? So my next entry here, if I'm going to the right, and I'm going out 1 unit, I'm now going to be at 1/4 of the height that it was previously. All right. If I go out 2 units, I'm going to be at 1/4 of the height of the previous value. So 1/4 of 1/4 is going to be 1/16, which is going to be really hard to show, especially like once I get past the, so I'm going to 1/4 of 1/4. Once I get more than 2 units out, it's going to be a little rough, right? So what we do is we assume the trend. I can't even, it's so zoomed in that I can't even make it look really like a 1/16. All right, but that's the idea. So it looks like it's decreasing. If we assume the next value would be 1/64, 1/256, and just keep going from there, you know, it's going to get a little crazy, right, in terms of trying to plot it. But if we assume the trend is going to lead us to the x-axis, although I can never really get it to look like an asymptote when I zoom in, then at least I have that part of the graph, right? But what I could also do is assume the trend works in the opposite direction. So if this value here is 1/4 of the previous y, which happened to be 1, and the same thing holds true for this, as I go down in this direction, then we can assume that at -1, there must have been some number that when we reduce it down to 1/4 of its value would give us a 1 as a result. All right. So 2, 3, 4, roughly. Actually, that's not even good. It's going to be a little, scale-wise, it's going to be a little further up. Something like that. We'll get the red back. All right, so it's going to be up around here at 4. Because the 1 needs to be 1/4 of the previous value going in this direction. So if you're going from left to right, you're going to use that base value or the common ratio and multiply it by the previous y value to get the next y value. If you're going the other way, if you're going left, so right to left, then you multiply by whatever the reciprocal is of the common ratio. Most people are like, okay, I'll just go left to right because it's easier to understand. But as long as you get it down, it's fine. All right, I'm just trying to clean it up a smidgy. A little bit better. So this is what the exponential function is going to look like in this case. And you'd say, well, it doesn't look anything like that. Well, that's because in this case, we have a fractional common ratio. All right. So if the common ratio is a whole number, so I don't think I wrote it here. If B is whole number, then we're looking at something that's going to be increasing. If B is a fraction, so between 0 and 1, so greater than 0. So actually, I'll just write that as a compound inequality. If 0 is less than B is less than 1, then it's going to be something like this. So it starts high, ends low. All right. Now, can you get all this off a calculator? Yeah. But just like with polynomial functions, you're better served if you at least try to understand why the relationships work the way they do. I think I got bit by the copy paste monster here. In number 2, it's same exact problem. So I'll have to change that in a sec. But before we do that, we want to talk about domain, range, and asymptote. Right. So the domain here, it extends to the left and to the right forever. So -infinity to infinity. For the range, it'll never hit 0 and it'll never go below 0. So we minimize it at just a smidge above 0 and it'll go on up to positive infinity. All right. So I guess we could get rid of the second example because that's a repeat. What I did in number 3, oh, you know what I can do? All right, that's what I'll do. I'll just make this f of x is equal to 2 to the x because I wanted to show you how an exponential function relates to the parent function. All right, so we'll look at f of x is equal to 2 to the x power. All right, so this is written as f of x, same thing that we did over here. F of x is equal to 1 times 2 to the x power. That 1 value, that's a, that's the y-intercept. All right, whatever the a value is, that's the y-intercept. Unless it's a transformed function, which we'll look at in a minute. All right, but the bare bones of an exponential, you know, like with a parabola, we could say the parent function is y equals x squared. For a line, y equals x, and then everything else is a transformation off of that. For exponentials, you could have a infinitely many parent functions. It all depends on what the common ratio is. So f of x equals 2 to the x is the parent function of any other exponential that has base 2 or a common ratio of 2. If just like in number 1, 1/4 to the x power would be the parent of any other function that has a base of 1/4. All right. But graphically, again, bring it in. At 1, we have a y-intercept. Let me not put the 1 there. I'll put it over here. As I go to the right, my common ratio is 2. So I'm going to double my height from the previous point. So 1 goes to 2, goes to 4, and I run out of room pretty quickly, so I won't even bother with this one here, because it'll go off the grid pretty quickly. So it's 2, 4, we're multiplying by 2 every step of the way, times 2, times 2, specifically the y values. Now, if I go the other way, then I would need some number that when multiplied by 2 would give me a 1. So that number must be 1/2. So it's basically going to be the same idea as the previous graph. It's just swinging the other way. All right, so at -1, we have a height of 1/2. At 0, we have a height of 1. 1, we have a height of 2. And at 2, we have a height of 4. If I went 3, then I would have a height of 8. 4, I'd have a height of 16, 32, 64, and so on. All right. But let me show you very quickly, graphically, as in on the calculator, just because it's not, it's different from the other functions, but you're still, if you could type in a function of any kind into the grapher, then you should be able to handle this too. I just figured it'd be nice to actually go over it. So starting from scratch, again, in the grapher menu, okay to add an element. You could go f of x if you want, because all of these are functions. Or you could just do what we've been doing, type in y equals, this time it's 2 raised to the x power. All right, 2 to the x power. And okay, locks it in to the graph. Oops. I guess long pressing doesn't always work for me. And that's what we have, which is ultimately what I put down on paper. All right. But you could trace along this and get points. At 2, you have 4. It hops over 3. So that's kind of aggravating, but you can keep going and get a sense of how it increases substantially. I'm only at an x value of like 13-ish. I'm at 14 and I'm already up to like 16,000. All right. So it has a very, very rapid rate of increase. All right. So it starts off kind of like a shallow, smooth graph, and then it just goes off the rails pretty quickly. All right. The domain and range for any of the parent functions are going to be the same. -infinity to infinity for the domain, and for the range 0 to infinity. All right, in every case. But for the transform functions, it takes on a little bit of a different form. So let me talk to you about the structure of a transformed function. All right. So again, the parent, we would say, is equal to, and I'll just put the general rule again, f of x is equal to 2 to the x. I'm sorry, not the general rule, the parent that we used in the previous problem. All right. So what's happening here is the x and y values are being manipulated. All right. So if I have a parent function, I can find the transformed. Now, specifically, these will be translated, right? So shifted. By using this form, f of x is equal to 2 to the x minus h plus k. H is the horizontal shift, K is the vertical shift. All right, horizontal, vertical shift. So if I match up, and I'll just kind of tuck it in over here, the given f of x 2 to the x plus 1 minus 3, I'm going to match up these two expressions to give me the h, and these two expressions to give me the k. All right. So I'm going to say x minus h is equal to x plus 1, and then k is equal to -3. All right. When dealing with these translated functions, it's very much the same as what it was when we did it with parabolas. Whatever is associated with the x, you just reverse the sign. Whatever is associated with the y. So x corresponds to h. Whatever the number is associated with that x value, you just flip the sign and that's your h. For the k values, it just is what it is. All right. But I like to do it this way so that people can at least see how to actually do it procedurally, just in case they don't get that concept. All right. So I'd subtract off an x from both sides. Cancels on both sides. You get a negative h is equal to a 1. So the h value would have to be a -1. All right. So this is going to tell me to shift left 1 unit and down 3 units. All right. So the down is coming from, I'll just highlight the negative sign here. So down is coming from the fact that that is negative. Same idea with left. All right. If these were positive numbers, you'd go the other way. All right. So what it's telling me to do is take my parent function and take every point on it, shift it left 1 unit and down 3 units. All right. So I'll just show you real quick. Let me get all of this, put it here. I'm going to get rid of the extra fluff. We have a horizontal asymptote. I've kind of like glossed over this a little bit, but I'll throw it in there now. This is my horizontal asymptote. All right. I'm going to take every single point here that I have, shift it left 1 and down 3. So, for example, I could start off with this one. I'm going to go left 1 unit, down 1, 2, 3 units. All right. So this point here goes here. All right. Then this second point, do that in red, is going to go left 1, down 1, 2, 1 more. So it's going to put it right here. The next point, get a green involved. The one at the origin is going to go again left 1, down 1, 2, and 1 more. All right. And then we have that one additional point there, which I'll cycle back to blue here. That's actually at a half a unit. Right. So if you want to count half boxes, that could be tricky. But if I know that I'm shifting everything down 3 units, so I'm only down 2 at this point. Let me just bring that a little closer. I can just take my horizontal asymptote and shift it down to -3. Oh, wow, really? Oh, because I used dash line. All right. That's okay, I guess. Just rebuilt it. All right, so my horizontal asymptote is now down at -3. All right, so my real points are, what color? I'll use a purple now. These are my real points. This one, and this one. All right, so if I make it approach the x-axis and increase, then I'll have my transformed function. It might seem like they intersect, or they might actually intersect, but it will happen with exponential functions. Eventually, they're gonna come together because they're gonna approach infinity. Just a question of in what way they approach infinity. So, it is possible that there could be an intersection. There could be, kind of a parallel kind of relationship, but that's how you would ship the points. So it gets pretty messy, but as you can see, but it's a nifty way of getting a sense of what the graph looks like rather than just popping it into a calculator. That being said, I'm going to pop it right into a calculator and really show you, because my diagram abilities are, as you can see, extraordinary. So 2 raised to the x plus 1 minus 3. All right. So red is my parent function, at least on the numworks. Red is my parent function, and blue is my transformed function. So let's take a look. And I'll do an auto here. All right. So I don't really like that. I'm going to change it from auto to -10 to 10. And for the y's, I'm going to go, well, I don't need to go -400, maybe like -4. Turn this off. And for the height, I don't know, maybe like 20. All right. And just move this over. This is what we're looking at. See, the blue part of it is shifted to the left and down. Right? It's not obvious on the left-hand side of the graph that it's shifted left, but on the right-hand side it is, because it's now to the left of the red curve. The red curve is the original, the parent function, and the blue curve is the one that was shifted over and down. All right. That's a little taste of the graphs of exponential functions. All right. And one of the reasons why I show this is because when it comes to logarithms, which can be, in terms of the mechanics of it, algebraically, it could be a little tricky. We have other methods to solve log equations, and they involve the calculator, but they do involve having a sense of what the graph of an exponential function looks like. All right. Now, the domain and range here. So looking at just the purple, it doesn't look like it goes to the x-axis as a minimum. It looks like it goes to that new horizontal asymptote. And actually, let me make a note of that. That's the new horizontal asymptote. The domain seems to go left and right forever. But the range, even though it goes up forever, it goes down below y = 0 now. It approaches but never touches a -3. All right. So if you like memorizing stuff, it's just basically whatever the k value is going to be the end point of your range. But I find it's nicer to just look at the picture. Also, if you're really kind of stumped or at a loss, and you need in a pinch to find the domain and range, you could go into the table and see what each equation is approaching as you go in one direction or another. So I'm at -10, and actually this is pretty good. If I start off at 0, you could see the values for the red, that's the parent function, is getting cut in half, in half, in half, in half, in half. And it does appear like it's getting closer and closer to zero. Whereas the blue, right? So it goes from -1 to -2 and so on. But if you go down or up the line here, we see that it appears to be getting closer and closer to -3. The number that it's getting closer and closer to, that's going to be the asymptote, right? No such luck the other way. It's not going to close in on a particular value. It's just going to get bigger and bigger without restriction, right? So on one side, you could expect it to go up to infinity or down to -infinity if it's a reflection. But on the other side, it should be approaching a particular value, which is the horizontal asymptote. All right. Now, in the next little section here, we learn about how logarithms relate to exponents. All right. And this is a very important concept because there's so much room for logarithms in math and also in the real world that it's, even though the concept itself can sometimes strike fear into the hearts of even the most studious of individuals, it's really not as difficult as I think the written word makes it seem. Right? You read this out of a textbook and it doesn't really do the concept justice. I remember the first time I saw a definition of logarithm, it was infuriating, right? Because the definition was a log is an exponent, right? So exponent will be the first word of the day, exponent, right? So exponent is the word of the day. So yeah, I didn't like that. I didn't like the idea that it was defined as just an exponent because I'm like, well, I know what an exponent is. Why give why give an exponent another name? What does it mean? What I look at a logarithm as is a process by which you can determine the exponent of an expression. So there's an unknown exponent and you want to make a determination of what that is. All right. So my example here, just go back to basics. We have something like, then I'll take you over to this example here. It's all, everything I just said is kind of written here. But like I said, as my preamble, it's like the written word doesn't do it justice. So what this is saying here is what power of x, I'm sorry, what power of 5 equals 2, right? Or you look at it and say, well, 5 is going to be raised to some number and get a result of 2. What's that number? All right. Now, this function is pre-built into pretty much every calculator, so we don't have to do what I'm about to show you, but it is a good kind of learning experience for anybody who kind of struggled with logarithms in the past. So I would look at this and say, right, 5 is going to be raised to a power, and it's going to give me a result of 2. So take a guess. Oh, I think it might be a 1. Oops, got to use the actual power button. Well, 5 to the first power is too big. It needs to equal 2. All right, so 5 to the first power is not going to get it done because I want to get a 2 as a result, and I'm way too big. So then you say, okay, well, maybe not 5 to the first, maybe 5 to the 0th power. Well, now that's too small. All right, so what I get from this is that x has to be between 0 and 1. It's just a question of where. Maybe it's 5 to the 1/2 power. Well, that's a 2.236. All right. So even that's too big. So now I would say, all right, well, scrap that. It's actually between 0 and 1/2. All right, because 1/2 gave me a number too big. So I'll try a quarter. now that's too small. All right, so I basically scrap this. Let me use a red strike through here. And say, well, now I know it's between 1/2. I'm sorry, 1/4 and 1/2. And in some cases that might be satisfying. Like I just needed a rough estimate of what it was. Well, it's somewhere in the neighborhood of between 0.25 and 0.5. So maybe like 0.35, 0.4, something like that. All right. But I want to be a little bit more precise. So let me say, I think it's going to be 0.4, 5 to the 0.4 power. Still too small. So I now know that it has to be between 0.4 and 0.5. I'm moving off the fractions now. All right. So it's somewhere in that neighborhood. So split the difference, raise it to the 0.45. All right. Between 40 and 50 is 45. Now I'm getting pretty close, 2.06. So I know that it's got to be somewhere between 0.4 and 0.45. So then I try something in between those two numbers. So I say 5 raised to the between 40, 0.40 and 0.45 would be like 0.42, 0.43. I'll say 0.43. So 1.99, I mean, that's almost right there. So now I know it's between 0.43 and 0.45. Maybe it's right down the middle, 0.44. Still too big. All right, so it's got to be less than 0.44. So between 0.43 and 0.44, so maybe it's 0.4, I'll go out to the thousands place, 0.435. Still too big. But not by a whole heck of a lot. So now I'll split the difference again between 0.43 and 0.430 and 0.435. I could say maybe it's 0.4325. I mean, that's right there. So 0.4325. Maybe it's even more precise than that. Maybe I'd say 0.4315. Still too big. Maybe I'll do a 0.4305. Just a smidge too small. All right, so on the low end, it's got to be something bigger than 0.4305 and less than 0.4315. And for most people, that's going to be satisfying enough where you'd say, all right, I have an idea. If I had to round it, I know it's between these two numbers. So I'm going to say that X is approximately 0.43, right? Because in either case, we're looking at, if we go to the nearest hundredth, in either case, we narrowed it down enough that in either case, it's going to round to 0.43. So if on the low end, it's 0.43, and on the high end, it's 0.43, then it's got to be 0.43. All right. So all of that, we don't want to have to do. So what we do instead is we convert it over to a log. So 5 to the x power equals 2 is the same as saying log base 5 of 2 is equal to x. All right. So what I use a technique called circular motion. I don't know if other people call it that. It's just what I call it. So if I have a log base 5 of 2 is equal to x, if I take that 5, work its way around the log, I'm going to get a result of 5 to the x is equal to 2. So in a logarithm, the subscript there is known as the base. All right. So this is my base. The base of a logarithm is always going to be the same as the base of the corresponding exponential. All right. What this is saying, when I say log base 5 of 2, all right, so log base 5 of 2, this whole expression here, I'm saying, and don't get thrown off by the word log, because it's just it's a term that somebody came up with a long time ago that represents this process. Could have called it anything. You could have called it the Timothy base 5 of 2. It really doesn't matter. All right, it's just a name, but it's telling you it's a recipe. It's asking, what power does 5 have to be raised to in order to equal 2? All right. So the key is these two numbers here. I'm overusing this highlighter. These two numbers here are the most important part, because it's saying, what does 5 have to be raised to in order to equal 2? All right. So going back to my example here, if I just type in log base 5, now in the screen, the home screen here, sorry, I just kind of went crazy clicking on it. You have natural log. You have common log. A common log has a base of 10. All right. So to get the log where you can change the base, you have to go into the toolbox, and you'll see the option here, log base a of x. All right. So tap on that. You type in the 5, type in the 2, hit OK, and you get 0.43067, rounds to 0.43. So instantaneously, we get the thing that it took me probably like 5 minutes to do by hand.
Wait, Professor, how did you get the little number, the log 5, the little number on the bottom?
So let me just show from scratch here. You go into the toolbox. So this button, and then go down to the one that says log base A. Then it'll bring you right to the base. So you put that little 5 in there, ordinary 5, but it becomes a little 5. Hit the right arrow a couple times. Then you can type in the 2. Hit OK, and it'll spit out the result.
Oh, okay, great. Thank you, Professor. Thank you
No
for
problem.
explaining. Thank you.
Yeah, so that's pretty useful, because I mean, I don't know how many old school people we have here that, you know, when you learned math, you learned it like calculator. What do you mean calculator? No, math is to be done by hand. We don't use calculators. Now, there is a school in the school of thought that I agree with. You know, like when you're first learning math, you should do it by hand so that you learn the math. But then you get to a point where it's like, well, I'm going to be reinventing the wheel every single time I solve a problem. So it would be really nice if there was a shortcut that'll do some of this stuff for me. All right. That's where things like using the calculator for a log comes into play, because nowadays it's an algorithm. You know, the same thing with trig. They use algorithms to come up with the those values, but and honestly, it's not always true. Sometimes they don't use algorithms. Sometimes it's just stored memory. Like they have a memory location in whatever device you're using that returns a 0.430676 blah 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 when log base 5 of 2 is inputted. Right. So long story short, it just means that the calculator's looking it up. Right. It's not doing anything special. It's just looking up the value in its memory. And to connect that with the old school way of doing this, if you're old school enough, you might remember something like log tables, where whenever you're solving a problem involving logarithms, you'd have to go to the back of whatever textbook you were working with, into the appendix, and find the log tables, and you'd look up, okay, log base 5 of 2, okay, that's 0.436 306. And same thing with trig. There were trig tables. If you wanted a sine of 31 degrees, you would look in the tables, right? It's all stored in calculators now. All right, so learning how to manipulate the calculator to get this information is really useful. If I don't want to say this the wrong way. If you just can't stand logarithms, there's another way to figure it out for something like 5 to the x equals 2. All right, but there will come up, if you're going down the calculus route, you're going to take calc 1, 2, whatever, you're going to need to know about logarithms. You're going to need to familiarize yourself with the log rules. But if you're in a pinch and you just need to solve an exponential equation, you don't have to convert it to logarithms. In most calculators, there's a solver function. This calculator is no different. So if you go to home, go to solver, option here is equations. Let me do that again. So solver, you'll see an option for equations. You'll also see finance. We're going to do a little bit with that later on in the unit, just because it's kind of cool. So more on that later. But for now, it's also part of the curriculum, but it's also cool. Learning how, financial applications of exponentials and logs. But yeah, TVM solver is pretty awesome. Useful for mortgages, anything, loan, interest-bearing accounts, things like that. So real applicable stuff. Anyway, click on or hit OK on equations. I have one in here, so let me get rid of that. Enter your equation here, which is 5 to the x is equal to 2. So hit OK and just type in 5 raised to the x equals 2. This will work for any function-based equation, meaning if the equation has a solution, it's based off of the left side of the equation being a function and the right-hand side of the equation being a function, and there is a solution, this will return that solution. All right. So you go to solve equation, solve the equation, hit OK. It asks you for a minimum and a maximum. It's basically giving the calculator somewhere to look for the solutions, right? This is akin to what I was doing here. All right, I'm going to check between 0 and 1. Well, nope. 0 and 1/2. Nope. 1/4 and 1/2, and so on. All right, that's the calculator is actually doing a process very similar to that. It's numerically going to determine what the solution is. It just helps it along the way if you give it a place to get started. So if I say, like I suspected initially, 0 and 1, type in 0 and 1, solve the equation, it'll give you the value. All right. Now, something to be cautious of, if I think the solution is between -1 and 0, which it isn't, no solution found in the interval. All right. A quick correction for that, if you know that there is only one solution. Now, that's why we talked about the graphs of exponential functions. An exponential function typically looks something like this. 2, so if I have something like 5 to the x equals 2, and actually, let me just do this in somewhere else, because I don't want to steal the room from here. If I have a graph of 5 to the x equals 2, that's the same as saying find the intersection between y equals 5 to the x and y equals 2. All right. So we have a general idea of what 5 to the x power looks like. It's going to look something like this. intersecting at 1. The line y equals 2 is going to be a horizontal line. A horizontal line can only intersect an exponential function at most one time. It'll never intersect more than once. Right? Because the only part where it ever go horizontal would be down here, and it would have to get out to infinity in order for that to happen. So it's not going to happen. Right? So if you know that a function is only going to have one intersection with another, then it doesn't matter what you put for the domain as long as it's sufficiently large. So you go to like negative 10,000 or negative 1,000 to 1,000, for example. Right? It's a safe bet that it's probably somewhere in between negative 1,000 and 1,000. So it'll give you the answer. All right. Let me just show you another one real quick. Let's say you have y equals, I'm going to use a parabola. So alpha 3 shift pi, and let's say x squared minus 4. All right. And I want that to intersect with something like, oh, actually, sorry. I got confused. I thought I was in the grapher for a second, but I want that to intersect with something like x equals -1. So I'm looking for any instance in which -1 would be equal to x squared minus 4. All right. So if I solve the equation, notice how there are two solutions. All right. So you just got to be mindful, just like the idea of exponential and a linear could have at most one solution. If I take a parabola and I look to intersect it with a line, that line may never intersect it. It may intersect it exactly once, or it might intersect it more than once. All right. So with cases of functions that turn around upon themselves, it could be a quadratic, it could be a cubic, it could be a quartic. Any of these could have multiple solutions, so we have to be on the lookout for that. All right. But we're focusing on exponentials. They can only have one intersection. So once you find the one intersection, you're done. All right. You don't have to go looking for another. You don't have to go wondering if maybe I missed one along the way. Once you find the one intersection, you're good to go. Now, for logs, though, there are properties that will allow us to simplify these logs fairly quickly and easily. We have the product rule, quotient rule, power rule. I already talked about a common log and a natural log, and then change of base, which is actually pretty irrelevant for us right now because our calculators have the ability to work with bases other than 10 or E. And what I meant by addressing it before, when I hit the log key, you notice how there isn't a base. That's an assumed base 10. I'll show you really quickly. Let's say I have log of 100. It tells me that that's the answer. If I go into the toolbox and select log and put a 10 in there as the base with a 100, it tells me that it's 2. Right? That's because these computations are the same. More commonly, people want to use a base 10 logarithm because powers of 10 are pretty easy to work with. Right? Less commonly, but also, I mean, more common than other bases, but not as common as the base 10 logarithm is the natural log. All right. So the ln key, if I wanted to find ln, let's say of 10, it's going to give me that funky decimal. Good thing about numworks is it'll also give you other forms of the value. All right. So you may not need it. Like maybe you didn't need to know that natural log of 10 is equivalent to natural log of 5 plus natural log of 2. But it's nice to have it. For right now, we're concerned with the decimals. But if I put in log and then type in an e, a lowercase e, And I don't know any other way to do this except to, well, I guess I could use alpha E. It's going to spit out the same value. What I usually do is I grab this e to the x right here because it's already got the e in it. And then I just knock off the power. It's like one less, well, it's the same number of keystrokes, but it feels like it's easier. All right. E is Euler's number, which is approximately 2.718. All right. So a base E logarithm is known as a natural log. All right. The properties of logs apply no matter what kind of log it is, whether it's a base 10, base 2, base 70, or base E, base 10, it doesn't make a difference. Right. The properties are still the same. So we have the product rule. We have the quotient rule. And we have the power rule to get us started. Right, because the others are just different forms of logs. What this is telling me, this product rule, is if I have something like log of 3x, so these are my examples here, you could write that as log of 3 plus log of x. I'm going to do this without a base. So I'm assuming a base 10 logarithm, right, just to kind of streamline it. If I have log of 3 over x, that's the same as log of 3 minus log of x. The power rule is kind of cool. I didn't mean for that to rhyme, but it did, and we're here now. The power rule helps us release values from exponents and make them into coefficients, multipliers, easier to work with. So if I have something like log of x to the third, that would become 3 log x. All right. So basically, I'm taking that exponent and I'm jumping right over that log. All right. So if you know those properties, which really isn't a whole heck of a lot, then you could do a lot with logarithms. So let me show you an example. These don't really cover that. Well, actually, they kind of do. Nah, I'll come back to these in a sec. Let me just jump to the top of page 10, page 14, sorry. I'm looking at number 10. You have something like this, log base b, so unknown base that we're just going to call b, of x to the 5th times y. All right. Because there is a product here, so I'll throw a little multiplication symbol in there to kind of exaggerate it. I can break this up into log base b of x to the 5th plus log base b of y. All right, so I'm breaking it up by the multiplication symbol, but that expands out into a log, the sum of 2 logs. Then I could apply, so that's the product rule. If I take that power of 5 and hop over the log and make it 5 log base b of x and leave everything else the same, what I've applied here is the power rule. And this would be, well, in this case, it would be the answer. That's really all it would be asking for. All right. It doesn't seem like it's much simpler than what you started with. Write each expression in terms of simpler logarithmic forms. It's expanded, but each individual logarithm only contains a single argument. Oh, that hopped away on me. All right. So you see here, this log here only contains an x. This log only contains a y. The original log contained a bunch of things. All right. So we want it to go from containing a bunch of things to just a single argument. So a single thing within the logarithm itself. All right. For convenience, I'm going to do number 12 just to show you. For this one, we have a quotient. Now, because it's made up entirely of variables, well, not entirely, we got the 1. It's not something you could just chuck into a calculator, right? So I could write this as, because I have a division here, I could write this as log base b of 1 minus log base b of c to the 8th power. All right, that's our quotient rule. All right, key fact. If you take the log of 1, regardless of what the base is, the result is always going to be equal to 0. All right, because again, we never want to lose sight of what it's really asking us. Anytime you see a logarithm, it's saying, what do I raise this to in order to get that? It would have to be 0. Right? But if you don't believe that, or you do believe it, but you're worried that you're going to forget it, go into the toolbox, grab a log, put in whatever base you want, and make the subject of the log 1. Hit OK, get a 0. Nah, it's a fluke. I'm sure that doesn't work all the time. So now let me make the base 8. Still a 0. Let me try it with a base e. Still a 0. No matter what you put in there, as long as it's a positive rational number, and even irrational numbers, but we're mostly going to focus on rational numbers, the result is always going to be equal to 0. All right. So this will be 0. Oh, that's not a marker. 0. Here I can hop the log and get -8 log base b of c. All right. And for this, I would say power rule. And also log of 1 is equal to 0, regardless of what the base is. So then just one last step, not really a step, it's just cleaning it up a little bit. You get -8 log base b of c. All right, we'll do more with these properties next time, but I did want to hop back in time here for a second and just do a couple examples on the previous page. As you probably are becoming more familiar with, I like to save some problems from one class to the next, just so we can kind of like have a nice bridge between where we've been and where we're going. All right. So then we'll do like 1 or 2 from each little section here. These will be easy because these are just, that's calculator work. Anytime you see round to anything, that's just code for put it in the calculator. I see a hand up. We have a
Yes,
question.
Professor, I was writing down and you had an X there. For number 12, if you scroll down, it says 8 log base of bx, or should it be
This one here?
no. The
Oh,
last
C.
equal sign.
Thank you. Appreciate it.
Sure.
Good catch. All right. So yeah, if you see round to anything, it's just telling you to put it in the calculator. All right. The only difference is what kind of base you're working with. The first one, so I'll actually just do number 7 while I'm here. Put in a radical 6. 4 decimal places, that's going to be approximately 3891. It gives you an alternate form, log of 3 plus log of 2 divided by 2. That's nice to know, but if we're asked to round it, we want the decimal, so it doesn't really behoove us to put any other form before we do that. All right. log base 3 of 17, about 2.5789. And then the natural log of 3, about 1.0986. Those were quick and easy. That's why I just did all three of them. When it comes to converting from log to exponential form, you see the questions 1, 2, and 3. You could apply the same exact approach to each one of these questions or equations. Take whatever the base is, swing it around, raise it to the power. So base power, and then that'll be the result. All right, so this is going to be 6 to the 1/2 is equal to radical 6. All right, there's nothing to solve here. It's just practice going from one form to the other. All right, so we had it in log form, we go to exponential form. All right, same idea with number 2. Start here, go here, and there. So 3 to the 2nd is equal to 9. Again, doesn't matter. Yes, it so happens that 3 to the 2nd is equal to 9, 6 to the 1/2 is equal to radical 6. It's not the point. It's just practicing going from one form to the other. I guess I could do it again for this one. E to the 3x by going from here to here, we get e to the 3x, and that's going to be equal to whatever's contained within the log, which happens to be e to the 3x. All right, so it's just practice going around the circle. Now, going from exponential to log form, I mean, I guess you could use a circular pattern, but what I like to do is first establish where the base is going to be, because the log of a base, a log of an exponent, the base of an exponential and the base of a logarithm are always going to be the same. All right, so I have a base 2 here for the exponential. So that means I'm going to have a log with a base of 2. All right, so if it's a base for one, it's a base for the other. And then what I like to do, it just as kind of a shortcut, the relationship between these two parts are always going to be opposite. So it's going to be log base 2 of 8 is equal to 3. But what I found a lot of people like to do is a little bit of trial and error, especially when you're not really comfortable with logs. That looked weird, so I fixed it. You just say, all right, well, I'm just going to take a stab at it, and I'll do that whole circular motion thing. So we can check and say, this is going to be 2 to the 3rd power equals 8. 2 to the 3rd, going, why does it do that? Going around the circle, 2 to the 3rd power is equal to 8. All right, so it's a quick way of checking. But again, it makes your life a lot easier if you recognize that the base of the exponential is the same as the base of the log. And then from there, if you accidentally, let's say you accidentally put the 2 here and the 25 there. When you go to check it, you're going to be like, all right, well, so that's 5 to the 25th power. Oh, wait, that's not what I want. You know, so then you'd realize it and say, okay, well, that it must be the other way around. So I'll put the 2 here. Oh, sorry, I already had that. The 25 here and the 2 there. And now when you check it, 5 to the 2nd equals 25. All right, I totally said I wasn't going to do all of them, and here I am doing all of them. All right, so log, the base of the exponential is the same as the base of the logarithm, so 10 of 110,000 is equal to -4. Now, this one actually happens to not be true. That's kind of the point. Again, we're just dealing with the skill of converting from one form to the other, but it is equivalent. It's just not mathematically correct because 10 to the negative fourth is not equal to 110,000. But I can check it by saying, all right, I'm going to start off with a 10. The power should be negative 4. And the result should be 110,000. And that's what we have here. It's just a different way of representing it. It's just because, you know, with math, science, doesn't matter. Whoever gets to a concept first gets to name it. So we have a name. They chose, it's logarithm, and we're stuck with it. But it doesn't mean that it has to be difficult. All right. I'm trying to remember who it was that we can blame for this. Did I put it in the notes? I used to have it in my notes so that we could all collectively blame the right person for logarithms. It's not Bornier. It's on the tip of my brain. Inventor, not really invention of logarithm. Oh, Napier. John Napier. Yeah, it was an IER name, but it slipped my brain there for a minute. All right, so that's where we're going to leave it off. Next class, we're going to learn about solving log equations. But if you want, before next class, you could give these problems a look, see if you can come up with the solutions. It'll kind of help when it comes to solving log equations. So, you know, it's not a requirement, but it's nice to have a quick look at something before the next class. All right. So I mentioned